We'll go from current slide. Okay. Let me get my pen set up. Okay. Okay, we're in chapter 17. And let me just go over a few things that I think I'm preaching to the choir here, because most of you are the ones who have turned everything in. Yeah. This. Okay. Let me just go to this. I am recording so people who aren't here can hear this as well. All right. Test 1. 2 people still haven't turned in test 1. I need those in. 2 people haven't turned in test 2. Now, not necessarily the same 2 people. Test 3, only 4 of you have turned that in, and test 4, most of you have now. So, chapter 17 test is going to be coming up relatively soon, so be sure to try to get caught up on that. Okay, any questions on anything we've covered so far? Okay. We're in chapter 17, and we did just a quick run-through of the early sections, and we didn't go into deep detail on any of this. We mentioned charges, what electric charges we have, okay? That was 17.1. 17.2, and these are very short sections, was induction. We'll talk about a different kind of induction later, so we didn't go into any detail on that. We did talk about last time Coulomb's law. That was 17.3, because just about everything else is based on that. There was only one example we did that. Then we talked about electric fields, and that followed Coulomb's law pretty closely, and there was just one example there. Now we're ready. I think that was 17.4. Yeah. So now we're ready for simple circuits. This is one that is, I think, closer to what y'all are going to be having to deal with. I don't know that for sure, but I got the impression from the course description that this was, 17.3, 4, and 5 are pretty important. And then we'll go over 6 real quickly, and then 7, 8, and 9. Okay? These are fairly short sections, so I think we'll get through them fairly quickly. All right, any questions on anything we've covered so far? All right. And okay. Now, what do we mean by a simple circuit? Well, there's 2 types of circuits. Anyone know the basic names for 2 different types of circuits in electricity? Okay. The lights up here are on one type of circuit. My computer, your computer, those kind of things are on a different type. Your telephone's on a different type. What are the 2 types of circuits? Anyone know? Second? I can't hear. No, sort of close though. Direct current as opposed to alternating current. Now, which of the things would be on direct current? Anything that has a battery. Your cell phone. The computer has a battery, right? Okay? Your automobile. All pretty much direct current. But wait a minute. I've got this computer plugged into the wall over here. Is it that alternating current? Yes, it is, but look at this. That box converts alternating current to direct current. This big wire coming in here, alternating current. The little thinner wire, direct current. So that's why that's operating in that way. This watch has a battery in it, direct current. Anything that's battery run, direct current. Anything that's generator run, alternating current. Well, wait a minute, let's go back to the cars. Cars have a generator. That's alternating current. But they also have a device in there, and different ones call it different things. The old days it was called an alternator. Nowadays, and then more specifically, a split ring commutator. And more specifically today, they use what they call a dual diode system that converts the alternating current made by the generator into direct current to recharge the battery. Okay? So that's what we mean by that. Now, what do we mean by an electric circuit? Key word there, circuit. What does that imply to you? Circuit. What word do you almost hear in circuit? What sounds like circuit? Circle. Exactly. A circle is something that's a closed loop, right? That's what a circuit is too. An electric circuit has to have a closed loop. Okay? And I'll draw you a very simple one that's in the book but it's not in the slide set. If you have a battery, I'm going to give you a little bit of introduction to this too. A battery is typically drawn something like that. Okay? A long line, a short line. And it may be multiple ones of them, it doesn't matter. Okay? But that represents a battery. The long line represents the positive side of the battery, and the short line represents the negative side of the battery. Okay? Now this battery is going from here down to a light. And I'm not going to draw the same symbol they do. The more typical symbol is something like this. And in general, that's called a resistance. If you put a circle around it, then you can imagine that as a light bulb. Okay, you don't need the circle, but it's a resistor. Okay, here we have a switch. And this is typically how we represent a switch. And then you close. Now, is that circuit closed? No, the switch is open. Is the light bulb going to come on? Not unless you close the switch, because the light bulb will not come on until this switch is closed. When that switch is closed, now you have a complete circuit. Your circuit is closed. Okay? Not quite a circle, but a circuit is closed. Now the light bulb will come on. Okay? Now, just because there's a gap here, that doesn't matter. A battery, okay, I'm wanting to get a little ahead of myself, but I think I'll go on and do that. The battery is your source of energy. Okay? Does anyone remember what units we used to measure energy? Several chapters ago. The units we used to measure energy. We had two different systems. Second, GPE is a type of energy, that's gravitational potential energy. So what units did we use to measure that? Okay. Okay. That was certainly included. Mass, GMGH, and mass was measured in kilograms, acceleration due to gravity in meters per second squared, and the displacement was measured in meters. So it's a kilogram meter squared per second squared. But we had a special name for that. Anyone remember? You ladies? Joule. That's a joule. That is exactly a joule. So, what is our source of energy here? That's the battery. Now, it's just not a source of energy, okay? We talked about this, I think, last time. What actually moves around the circuit? This is not a fair question because it's not quite the important thing, but for right now it'll count. The charges. And does anyone remember what we measured charge in? Named after a French physicist. Coulomb. Excellent. Okay? So, what your source of energy is how much energy you give each charge carrier. So your source of energy is your battery. Here is your battery. And what we measure the battery strength in is in volts. And what a volt is a joule per coulomb. A volt is a joule per coulomb. Okay? Now, something a little unusual about voltage. Remember, for instance, you were giving me GPE here, right? What we call those letters there, M, G, H, those are parameters. They represent the units you're trying to measure. Mass is measured in kilograms. Gravity is acceleration due to gravity, meters per second squared. Height, measured in meters. Those are the parameters, M, G, H. The units are kilogram, meter, seconds. Okay? Now, with voltage, the symbol, the parameter representing voltage, which is your source of energy, that is a V. And guess what units we use for volts? V. Okay, that's the one and only that I can think of that we use the same letter for parameter as we do for the unit. And by the way, it's a capital V. What does that suggest to you? Named after somebody. And that somebody was an Italian scientist named Alessandro Volta, V-O-L-T-A. Okay? He basically, you can't say he made the first battery, but he studied batteries. The first person to do so in extensive studies was Alessandro Volta. Actually, I'm sure people had discovered but not known what a battery was before, but the first guy who documented that he had in some ways isolated a battery was not a physicist at all. He was an anatomist. He studied anatomy. You've done that, right? Okay? His name was Luigi Galvani, G-A-L-V-A-N-I, another Italian. Okay? Now, like I said, he was an anatomist, and he was in his lab studying the tissues that occupy a frog's leg. Okay? The vascular tissue, the neural tissue, the muscular tissue. He was in there studying that. Now, he had had a dead frog for probably a long time. It had been in formaldehyde so it wouldn't decay. Still stunk badly enough, I'm sure. Formaldehyde's not any favorite. But this dead frog had been in the formaldehyde probably for weeks. Okay? He cut off his leg so he could study the tissues. Okay? So he had him a little set of tweezers here, and he also had a pick. And he was trying to hold the frog's leg with the tweezers very gently, and with the pick, separate the fibers from the muscle and see if he could identify those that were arteries and veins and those that were things. So he was here very patiently and carefully trying to pick his way through the frog leg, and it twitched. Talk about someone who was pretty shocked, okay, literally, okay? Because he said, wait a minute, this frog's been dead for weeks. Its leg's cut off. It's not even part of the body. And here it moved. Have I found the source of life? I mean, that would be any anatomist's dream, right? And he thought somehow he had found how a dead frog leg separated from the frog could move on its own. Twitch, okay? Very definitively twitch, okay? Here's the deal. He didn't realize this at the time. He didn't understand it. Probably many of us wouldn't either. But it just happened to be his tweezers were of one type of metal, let's say steel, and his probe was copper or something else. So here he had in his hand two types of metal, and the frog leg was filled with formaldehyde, which would make a good electrolyte. So what he had was a battery. He didn't realize that, but the two different metals separated by an electrolyte conducted a charge. And when it conducted the charge, the muscle twitched. Because what makes our muscles twitch? We are electrical machines. Have you ever thought of it that way? That's exactly what we are. Our nervous system, our neural system, is a series of conductors, those are the nerves, and two different charges. We have sodium and potassium. Sodium and potassium on the periodic table, one right above the other. Sodium's here, potassium's there. They're very similar. They're actually metals, but they're pretty soft metals, but we don't usually think of them that way. Very close in their electronegativity, but just enough difference that the difference between those carries a charge. And that's how we see, that's how we speak, that's how we hear, that's how we pump our blood, that's how we do everything we do, is through those little neurons moving around. So Galvani thought at first he had discovered life, and then the more he tried on it, he found out, no, he really didn't. But he either published it or told his friend, or somehow Volta found out about it and decided to study it further. And he did extensive studies with two different types of metals separated by moistened material that contained an electrolyte, and he was able to produce a voltage difference, and that voltage difference was capable of carrying a charge. That's what a battery does. The voltage difference gives energy to the charges, joules to the coulombs, and sends the energy moving on its way. Okay? Probably way more than you wanted to hear, right? Okay. So what we're dealing with here, and it's so good you mentioned gravitational potential difference, potential energy. What we're dealing with here is electrical potential energy. You might call it EPE, but we usually don't. We just call it voltage. Electrical potential energy. Now, it's not joules. It's joules per coulomb. The energy per unit charge. Okay? So we talk about a difference in potential. That's what the batteries produce. Okay? They have a picture in your text, if you have that, of a, and by the way, in a battery, that's created with chemicals. Okay? You have inside the battery a carbon rod, and carbon is pretty good about giving up, receiving electrons, giving up electrons, and zinc is a metal, and it receives electrons. Well, one way or another, let's see. Yeah, the zinc can receives the electrons, and the carbon gives up the electrons. So the carbon rod winds up being positively charged, the zinc can negatively charged, and in between that is that electrolyte. You'll see paper in there. That paper is soaked with a material that transmits the charges. Okay? Now, we call that a dry cell battery, but it has to be moist inside, otherwise it doesn't work. It's just not a wet cell battery like your car battery is. You ever mess with your car battery? If you open those plugs at the top, you see there's a liquid down there. Don't mess with that liquid. You know what that liquid is? Sulfuric acid. Okay, one of the strongest acids out there. And what it's doing, it's transmitting lead from one plate of the battery to lead sulfate, the other plate of the battery. There's your potential difference. And usually you have 6 sets of plates there. Each potential difference between is 2 volts. 6 of those would make 12 volts, and that's why it's a 12-volt battery. New ones are about 12.4 volts, but whatever, close to 12. When they get a little older, they may get down to 11, 11.5, and at some point, then they're not strong enough to do what needs to be done. But that's what your battery is doing, providing potential difference. These dry cells, like you see in your book, they're usually around 1.5 volts potential difference. That means 1.5 joules is given to every coulomb of charge. Now, I'm trying to remember. I may have to come back. Yeah, I think I'm okay. All right, here's the figure in your text, which shows sort of the same thing I was just talking about. Let me go from current slide. Okay. Here is your battery. Okay. They made it a big battery. Okay. Now.
Sorry.
Oh. Okay. This battery is indicating. I kind of resent this a little bit. Well, this isn't how it's usually done. But there is a problem here. Not a serious problem, just a little issue. I think I may have mentioned before, I know I did, that you have two types of charges, right? Anyone remember? Positive and negative, okay? And these were sort of arbitrarily assigned. I think I've read that it was Benjamin Franklin that did it. He just decided to name the charge on a proton a positive charge and the charge on an electron a negative charge. Just sort of arbitrary. It didn't really matter, but just two different charges. Unfortunately, it kind of hurts, okay? Not bad, not serious. And that's why they say here the high energy side is the negative side. Wait a minute. Usually we have positive being high, negative being low. Well, the reason these are backwards here is because electrons are what do the moving, and they're negatively charged, so you have to reverse the order. So they talk about electron flow this way, okay? The high energy side being the negative side and the low energy side being positive, which seems totally backwards. And it is. If Benjamin Franklin had just flipped a coin and said it the other way, we would be happy campers, okay? But they're just names, positive and negative, okay? One gives charges energy to the electrons, and the other pumps the energy. This is a chemical reaction that's doing that, and that's what's giving the energy, increasing the energy of those charge carriers. Now, quite often, this book doesn't do it, but quite often we'll refer to the charges going this way. Let me get my pen back. Okay. We'll say the conventional current. And that means the direction a positive charge would move if positive charges were moving. Positive charges don't move. Positive charges are the protons. They sit right where they are. They don't move much. Now, I'll take that back a little bit. Because remember I said in your car battery, that's sulfuric acid and lead sulfate. Well, in that, your lead and lead sulfate is ionized. The lead is a +2 charge, +2 or +3, and the lead sulfate, or the sulfate, is a -2 or -3 charge. So inside the battery, the lead goes this way and the sulfate goes that way. So both the positives and negatives go because those are ions. They're not individual charges. They're ions that carry the charge. Okay? And that's what gives the energy to the battery. And then the electrons move this way or the conventional current moves that way. Either way you want to do it, it doesn't matter because you just have to have charge moving. But the charge is moving only one direction. That's what makes it direct current. And here's your load over here, which is the bulb. And I don't know if you've ever noticed this about a bulb. I don't have one in here. But when you unscrew a bulb, you'll see there's a black sort of button at the end with a silvery type, or maybe even bronzy, or some type of thing in the middle of it, black around it. Okay? And you have most of your bulbs, the screw-in part, that's metal around there, right? Well, this has to be touching that metal, but the black keeps it from touching the other metal, so you have the source of electrons coming in here, going through the filament, going out here. There's your complete circuit. If you didn't have that in there, the bulb doesn't light. It just goes directly from here to there without lighting. So that's how the bulb is made. Okay. Now, the analogy to this is a water pump. Here you have a pump. Turn on the juice, whatever kind of pump it is. It could be a a mechanical pump that you turn by hand. It may be an electric pump. It could be any kind of pump, but it pumps the water from the tank up to the tower, okay? This looks like the peach out at Clanton does it, okay? There's the tower, the water's up here, then gravity pulls the water down, and here it turns a turbine, and that could be producing electricity, it could be running your radio, it could be doing whatever it's going to be doing. That's where the energy is spent. The water goes back here, it pumps it up again. Okay? That makes sense, kind of, doesn't it? Okay? Now, what's analogous to what? The pump is just like the battery. This is what gives energy. Here it's gravitational potential energy to the water, right? Here it's chemical energy, giving electrical energy to the charges. So many joules per coulomb. Okay? What are your pipes here? That's kind of like your wires here. Okay? The turbine, which is producing or using the energy, that's your light bulb. That's the load there. Okay? And that's your circuit. The battery gives energy to the charges. Oh, the charges are like the water. Okay? That's what carries the energy. Up here it has more energy than it does down here. Okay? Here it has more energy than it did down there, the electrons. Okay? So this is the analogy, and they call it the water pump analogy between electricity and things you're more used to. Okay. Before we go to that slide, let's talk about those charge carriers. I wish we had some slides here. Let me go back. It's sort of a pain in the neck to have to do this, but we got to do it, I guess. Okay, and I got to get my pen back. Okay. Let's look first at that wire. Simple wire. Okay? That's called your conductor. It conducts the charges through the circuit. The conductor. Okay? It's usually the wire, and literally it conducts the charges through the circuit. It's the material that does that. Usually this is copper. Copper is not the very best conductor, but it's a very, very good conductor. The very best conductor we have is silver. So why don't we use silver in our wiring? Yeah, it's way, way too expensive. But that's not the only reason. Silver is a brittle metal, and it's hard to bend silver and get it to go where you want to, where copper is very ductile. Okay? This is copper wire, and here you can do just about anything you want to it. Okay? No problem. Silver would be very stiff. Not good that way either. And the difference is very, very little. Silver is better, but copper is quite good. The next best is aluminum. And aluminum, the difference between silver and copper is like this. The difference between copper and aluminum like this. You don't want to use aluminum. It is not as good a conductor by a big part. Okay? Now, what makes a good conductor? The ability to carry the charges without much interference. That interference we call resistance or resistivity. Silver has a very low resistance or resistivity, and so does copper. Aluminum has a low, but not nearly as low as the other two. Now, what's this stuff on the outside of the wires? What do we call that? Yeah? Yeah? What's that? It's probably rubber or a synthetic. Why do we have that there? Okay, yes, protect you from electric shock. Why is that? Because this rubber is a terrible conductor, making it a great insulator. So the inverse of a conductor, or reverse of it, is an insulator. Okay? Have you ever noticed on power poles, okay, you know, the arms are out there, the wires are running down. They usually have, in the old days it was ceramic material, and that's what the wire ran through. Ceramics are terrible conductors, fantastic insulators. Now I think they probably use more plastics than ceramics, because ceramics can break easily and the plastics can't. But those are insulators. Like I said, this probably isn't rubber anymore. It's probably a synthetic plastic-like material that does. Remember when I said at the end of the light bulb, that little black ring? Insulator, a plastic insulator that keeps the charge from short-circuiting across it. Okay? So there's your insulators. There's one other type of material called and you probably have heard the word, I don't know if you know what it means, semiconductor. What in the world does that mean? What does the word connote to you? It sort of carries charge, and sometimes it sort of doesn't. Okay? It's a semiconductor. And given the right conditions, it conducts it very easily. But other conditions, it might not conduct at all. Okay? And guess what we use those for? Intel inside, Citrino inside, the semiconductor industry. Silicon Valley, out in California, this is your semiconductors. This is what makes computers and chips and cell phones and everything else possible. Semiconductors. They conduct a small number of materials called semiconductors, fall between conductors and insulators in their ability to conduct electric circuit, and they go on talking about it. Okay. There is one other type of material, and that's called a superconductor. Okay? Now I said silver was our best conductor, normal, stuff, but there's actually some things that are better than silver. And these are your superconductors. And these are fascinating materials because they will conduct electricity with absolutely no resistance at all. Unbelievable. Problems with them. Oh, and by the way, if you go and study the Nobel Prizes awarded in physics, go through the list for the last century or so, you'll probably find at least 4 Nobel Prizes awarded to people who studied superconductors. They are that incredible, okay? The trouble is they haven't found a material to be a good superconductor that's not extraordinarily cold. You have to have it down just a few degrees Kelvin. That's a few degrees above absolute zero. Incredibly cold. So therefore, it's hard to deal with them. You have to spend so much energy keeping them cold that the advantage of being superconductors is almost wasted. Okay? But that's the 4th type of material, superconductors. It's a material that continuously conducts electric current without resistance when cooled to typically very low temperatures, usually near absolute zero. Heikki Kammerling-Onnes discovered the first superconductor in 1911, shortly after he discovered the flow of electricity at temperatures just below 4.2 K, the boiling point of helium. That's how cold it is. So that's what we're dealing with. All right. Now, let's go back. Sorry about this. Let me go back and forth. All right. Remember the previous slide that looked sort of like this? And this one labels it too. What's the light bulb called? Okay, let's go back and review. The battery is your pump That's what gives the energy to the charge. The wires are your conductors of those charges, carrying the energy where you want it to go. The light bulb, or whatever else it is, the computer, your projector, whatever it is you're fiddling with, that's the load. That's what's using the energy that the charges are carrying. Producing light in this case, heat perhaps, moving your charges around. That's your load. Okay? You have to have that for a circuit to work. If you just had a power supply, a energy source, and wires with no load, those wires are going to get very, very hot because it's moving charge really, really quickly, and then you overheat and things don't do well. The load is what uses the energy. All right? Now, the current is the rate of moving charge. So let's get that down. The current, let me get my pen back. I have to do this every time. Current, okay, is the, and we did this from the very first class, I think. Once you identify something like distance or displacement, first thing we did, well, let's take the time rate of change of that. And when you did that, you got a velocity or a speed. Well, let's take the time rate of change of that. You got an acceleration. Well, we identified at some point momentum, or maybe we did or not, but time rate of change of that, that's a force. If you have energy, the time rate of change of that is power, okay? One of the favorite things physicists have, take the time rate of change. Well, we just came up a short time ago with charge. Well, guess what current is? The time rate of change of charge. Charge per unit time. Okay? What do we measure charge in? You answered it earlier. Coulombs. Time. Second. And current is measured in amps. And by the way, that's a capital A. Wonder why? Named after somebody. I think it was Louis Ampere, I believe it was, a French physicist. And so the charge is often called an ampere, but the short title for it is amp, okay? And the symbol is capital A. Current is measured in amperes, that is charge per time, coulomb, that's a capital C, per second. Coulombs per second, that is your current. 1 amp is 1 coulomb per second. Now remember back when we were talking about charges, the fundamental charge is that little e, the charge on a single electron or single proton. That's so incredibly tiny, you have to have, so many quadrillion of those to make up 1 coulomb. By the way, capital C after Charles Coulomb. Okay. All right. Now, this is the slide. No, it's not. It's close to it, but not quite. This is a circuit, and we call this a series circuit. I thought this was one in the book, and it's not quite. The one in your book is one I've already talked about, okay? I'm going back to this one. There's your battery there. This is the one on page 463. If this is the plus side, that's the minus side. We talk about a positive current flowing this way. We often call that the conventional current. And why it's called conventional is in every other field of physics, you always go from high potential to low potential. Everything does that. I'll hold the book up here in the air. That's high potential. I drop it. That's low potential down here. Always moves from high to low. Okay? Except in electricity when there's electrons moving the other way because they're negatively charged. So this is what it's showing. The positive charges would go this way if they actually moved, and the negative charges, the electrons, flow the opposite direction. That's the figure there. And they do mention Alexander Volta here, which we've already talked about too, that the potential difference is energy or work per unit charge. So volts is equal to joule per coulomb. I'm sorry, I got ahead of myself there. That was Alessandro Volta. Now this book uses another, it's an old symbol. It's called EMF, okay? That used to stand for electromotive force. Until they realized, I guess they always realized, but they just called it that, it's not a force at all, okay? It's energy per charge. That's not a force. It's related to a force, but not. So now they don't call it electromotive force, they just call it EMF, but don't tell you what that stands for. It's better basically just to avoid that. But the parameter for that, these are parameters now, is E. Now that's sort of unfortunate there too, because in the last section we did before we left last week, we called E electric field. Here we're calling it electromotive force. We use too many letters over and over for different things. But your potential difference, that's what it's called. In fact, often you'll see this called the delta V. Delta meaning difference in, change in, the change in voltage. That's what's important. Remember, just like potential energy, you mentioned that before, gravitational potential energy. It really doesn't matter where your zero potential level is. What you're interested in is the change of energy. I could hold the book up here. I could drop it onto the stool. That would be my zero. Or drop it onto the desk. That would be my zero. Drop it onto the floor. That would be my... Or hold it out the window and drop it onto the ground. You could have your zero level anywhere. What you're interested in is the change of potential energy. That's what we're interested in here, the change of that voltage, potential energy. So, now, let me just glance and see what the next slide is. Now, okay. Let me go back to, sorry. Okay. Now let's talk about that other thing that we were hinting at before, and this is resistance. Let me get my pen back. Okay, we talked about a conductor carries a charge easily with very little resistance. I use that term. An insulator hardly will carry a charge at all. It has incredibly high resistance. When we talked about superconductors, they have zero resistance. The charges just move and move and move and move without even a voltage once you've got them going. Okay? So what is resistance? Well, it's the opposition to the flow of charge. That's the best way. I was trying to think of good words to use. That's what the book does. Now, the unit for resistance was studied by a German physicist named Georg, almost looks like George, but it's Georg Ohm. Okay? Georg Ohm studied resistance. And he found there's a relationship between the amount of voltage you supply and the amount of current that is produced. It's a direct relationship, a proportion, and if you add the proportionality constant, that gives you the resistance. Okay? So in other words, voltage is equal to some constant times current. And by the way, the parameter for current is capital I. Why? I do not know. Okay? And voltage, remember, the unit and the parameter is V. Okay? So if you're saying voltage is proportional to current, then when you put in the constant there, you give it voltage is equal to K times the current. Okay? This K is your resistance. Okay? They give that the symbol R. So quite often you'll see V is equal to IR. And we'll give a name to it. That's Ohm's law. Now that's the section we're not going to do, but there it is, Ohm's law right there. Okay. Now, we need a unit for the resistance. Georg Ohm studied this. So guess what they named the unit for the resistance? Ohm, of course, okay? Now what symbol should we use for ohm? O? Sound like a good symbol? Called capital O? Well, what if we had 5 ohms of resistance? What's wrong with that picture? It looks like 50. So we can't use O, capital O. It looks too much like a 0. So quite often when our alphabet is insufficient, we go to the Greek alphabet. Well, the Greek letter for O in our alphabet is omicron, which is O, okay? That doesn't work either. But the Greek alphabet actually has 2 letters. The one that represents our O is omicron, and that looks just like our symbol O, okay? But the other letter in the Greek alphabet that is an O-type word, anyone know? Omega, you've got it, okay? Anyone know what letter in the alphabet that is? Greek alphabet? Yeah, it's a horseshoe thing. The Greek letter omega looks like that. That's the capital Greek omega. The little Greek omega looks like a W, okay? Don't ask me why, but the capital O, and because it's named after someone, they use the capital, so they did use that. But I bet you all of you, or most of you, or some of you anyway, probably could tell me what letter in the Greek alphabet was omega if you thought about it real hard. What's the first letter in the Greek alphabet? Anyone know? Alpha. And guess what the last letter is? Omega. Have you ever heard the phrase, the alpha and the omega? The beginning and the end. The first and the last. That's what it means. Omega is the last letter in the Greek alphabet. Okay? Now, good deal. Got a test? Good deal, thank you. There it is. So, they decided to go with the omega as the symbol for an ohm. You're not going to confuse that with an O or a 0, okay? So they used omega. Now here's a really dumb thing, okay? Just shows how dumb physicists are. Resistance is measured in omegas. There is another term that's really related, closely related to resistance, and that is the one of conductance. Resistance is the tendency to resist the movement of charge. Conductance is the ease with which charge is moved. And conductance is 1 over resistance. Okay. Now, they needed a unit for conductance. And it wasn't just one guy who used it, a bunch of people used it, so it wasn't really named after anybody. Or maybe, I mean, we'll see. What unit could they use for conductance then? Any idea? Here's what they wound up with. They called the unit for conductance a mho. A mho? Is that as Three Stooges mho? No, that's not what we're talking about. Where did they get that unit mho? No mho. No, not that. Where do they get the unit mho? Remember, it's 1 over resistance. Any ideas? You're almost going to slap yourself when you realize it. Say again? Yes! It's ohm spelled backward. See? M-H-O. Boy, physicists are crazy, aren't they? Okay? They named the unit of conductance, which is 1 over resistance, the mho. So what symbol can we use for a mho? We can't use M. They use that for meters, so we don't use that. They can't use a capital M because that stands for mega, you know, and that doesn't work either. What symbol will we use? And we can't use mu, they use that for micro, so that's out of the picture. What symbol can we use for omega? For mo? Remember, conductance is 1 over resistance. Here's the symbol they use, which is nobody's symbol anywhere. That's not in anybody's alphabet. It's simply an omega upside down because it's reciprocal of an ohm. So, physicists are crazy. Okay, that was all beside the point. Okay, let's look at some of the characteristics of resistance. I think I'll go to a clean page. What are things that contribute to resistance? Okay, 4 major factors. And I don't like the order in which the book does them, so I'm going to do them in a different order. The first is the material. Okay, the material, as we said, the very best common resistor is silver. Next best is copper, but even more common, so close to silver you can use it instead. Next would be aluminum, then you get iron and some of the others, and after a while you get really lousy. But the material is a big contributor to your resistance. Okay? The characteristic is the resistivity. Resistivity. I have a hard time spelling that. Okay? And that resistivity is given the symbol rho. Don't ask me why so many different things use rho. It's resistance per unit length. And that's probably where the rho comes from, resistance per unit length. Okay. Another characteristic, and it doesn't matter which order you do these, I'll go with their second, is length of your resistor. Okay? Now you tell me, what do you think would be the greater resistance? A long wire or a short wire? Thinking that all wires have some resistance to them unless they're superconductors, but those are super cold, so we don't mess with those. So the longer the wire, the more opportunity for resistance, right? Now, I don't know if you've ever done this before. When we were burning, we had a really bad ice storm hit us over in Georgia, and the 4 pecan trees that are in front of the 2-bedroom bungalow that we built over there just lost so many branches, and they were down on the ground and stuff, and we had cut them up, hauled off the bigger ones, but the little pieces we were just going to burn in the pasture there, okay? And when we were getting set to burn, I ran the hoses from the house all the way down to the field, as long as I could, as many hoses as I could connect to each other so we could control in case the fire got out of control. But guess what happened? When you ran it that far, turned on the water went, you know, it hardly came out at all. Why? There was so much resistance in the hose to the flow of water that the strength with which the water came out was pathetic. Really pathetic. You couldn't put out much of a fire with that. So anyway. All right. So the length determines resistance as well. Okay? Another thing is cross-sectional area. Okay? Now, I think I've used this example before. Have you ever gone to one of the fast food places in the morning and bought a hot cup of coffee so you can make it through the day, or at least through the morning, or at least drive to work or whatever, and they gave you one of those little bitty swizzle sticks with a tiny little hole in it, and you could sip the coffee through that because it's really hot and you didn't want to sip too much, right? Okay, you know what I'm talking about. Okay? Now let's imagine you went to that same fast food place later in the day and got you a milkshake. And what if they gave you a little bitty swizzle stick then, and said, enjoy. You're going to blow your eardrums out trying to suck the milkshake through that little swizzle stick. Why? Because the cross-sectional area is so tiny, the resistance is huge. Coffee, hot coffee will go through it okay. You don't want that very fast anyway. But a thick milkshake is not going to do it at all. In fact, you need a straw that big, right? And even that, you sometimes have to really pull at it. So cross-sectional area, the bigger the area, the less resistance, the smaller the area, the more resistance. The longer the length, the more resistance, the shorter the length, the less resistance. The type of material, that also matters. There's one other, and that's temperature. That's what they list first in the book, but I wanted to save that for last. Now, how do you think that resistance deals with temperature? Remember what our superconductors are? Incredibly cold. So the higher the temperature, the greater the resistance. The lower the temperature, the less resistance. Now, if you think about that, it sort of makes sense, because at higher temperatures, all the molecules and everything are moving faster and bouncing around more. So for a current to go through, it's going to be more resistance, right? Now, nowadays, in fact, in a few years, I won't be teaching anymore, but there will be, this will be a hard example to explain to students. Y'all know what an incandescent light bulb is, right? The regular old light bulbs. Okay, you've seen them, right? Okay. In probably 10 or 15 years, no one will have seen very many incandescent light bulbs, because they went from incandescent light bulbs to compact fluorescence, and now they've gone to LEDs. And that's what you get most days now. Most of your stores, Home Depot hardly sells any incandescent light bulbs anymore. We have a few at our house, just they haven't burned out yet. But if you think about that, have you seen the clear ones that you can see the filament in there? What did you notice about the filament? Describe it for me. A little wire. You really said it right. That wire, the thickness is probably no more than a hair. I mean, it's just a tiny little wire making a very small cross-sectional area, which means a lot of resistance. Okay? What else do you notice about that filament? Have you seen them? They're in a coil, right? Have you looked at them in those clear bulbs? Look at them sometime. If you got a clear bulb, look at it. It's a little bitty coil, and it just goes like this. If you were to straighten that out, it's going to be really long. More resistance. The length. Okay? Now, what you probably don't know, the material. That's probably originally, I think, who invented the light bulb? No, Thomas Edison. Thomas Edison. And he went through so many materials and so many different ways to do it. Finally landed, I think he's the one that landed on tungsten. Tungsten is a metal, but its resistance or resistivity is way down from what? Silver, copper, aluminum, iron, it's way down there. Very high resistance. So what he had was a material that resists very long length, that little coil. It's very tiny cross-sectional area. And that's what heats up. And by the way, you ever fill a light bulb up that's been running for a while? Burn your hand, okay? Because it gets really, really hot. What it is, it gets so hot that it glows. And that's the other thing tungsten did. It will glow whitish light when it gets very, very hot. And that's why. Now, I want to ask you a question. Most of the time in your life, when you have had a light bulb go out on you, when did it go out? When you turn it on, exactly. Because when you turn it on, the light bulb is cold, right? Not hot at all. And the cooler the temperature, the less resistance, so more charge goes through. And if the filament's been in there a long time, and all the time it's been heating up and glowing like that, it's losing, electrons a little bit. It's just losing material. It's sort of evaporating away. And when you turn it on and that big charge goes through, it was fine when you turned it off because it was hot then. It had more resistance. But when you turned it on cold, now more current went through because of lower resistance, and it blew. And that's exactly why most of the time your light bulbs go out. So you see all four of those you can think of in terms of your light bulb. Okay? It's a material that has a low resistance, tungsten, long length in a coil, small cross-sectional area about like a hair, and the temperature depends on the, more likely to blow out when it's cold. Okay. Now, they do use this formula, though it's not really all that crucial, but here's one they're going to give you. Your resistance, that's R, is equal to rho, that's your resistivity that depends on the material. Okay, tungsten has a very high resistivity, copper has a very low resistivity. Okay, but that's dependent on the material, times the length divided by the cross-sectional area. The longer the length, the greater resistance. The smaller cross-sectional area, the greater resistance. Okay? Now, here's what the example 1 is asking. I think we have room to write it here. Find the resistance, that's R, resistance is R, of a copper wire. So you got a copper wire. We're going to have to look that up. 20 meters long, 20.0 meters long. That's one long copper wire, okay? That's its length, okay? With a cross-sectional area, so the area is 6.56 times 10 to the minus 3 centimeters squared, okay, at 20 degrees Celsius. Now there's a temperature we've not really talked about that much. Now I said we're going to have to look it up, but they give it to us. The resistivity of copper, that depends on the material, is at 20 degrees. This is resistivity at 20 degrees. So that's where that comes into play, 20 degrees Celsius. By the way, what is 20 degrees Celsius? Anyone remember? About what? Room temperature. Okay? I don't know what the temperature in here. I think it's a little above 20 degrees Celsius, but it's right. 68 degrees Fahrenheit, 20 degrees Celsius, right at room temperature. So at room temperature, the resistivity of copper is 1.72 times 10 to the minus 6 ohms centimeter. Okay? That's what we measure resistivity in. It's resistance per unit length. So they got the unit wrong. It's ohms per centimeter, not ohm centimeter. Okay? Yeah, can't be. Okay. Otherwise, the units don't work. No, I'm wrong. It is ohms. Ohm centimeter. It's not per centimeter. They have it wrong in the book. Okay? It says resistivity is the resistance per unit length of a material. It's the resistance of a unit length, not per unit length. They said the word wrong. Okay? So, my eraser's not erasing. It's not erasing. It's not, there it goes. Okay, it is ohm centimeter. Okay. So, what is the resistance of that copper wire? 20 meters long, that's all one long wire. Area of 6.56 times 10 to the minus 3 centimeters squared at 20 degrees. Okay? Now, I don't know if you recognize it or not, but we have a little it looks like we may have a little bit of a problem, but we really don't. Well, we do too. Here we have a length in meters. Here we have an area in centimeters squared. Here we have a resistivity in centimeters. Guess what we got to do before we can plug in anything? Get our units. And which way you want to go? Meters to centimeters or centimeters to meter? Yeah, let's go meters to centimeter because you got centimeters in two places, meters in one, so let's do that. So let's start with our 20.0 meters, and we need to convert that to centimeters. Okay? What's the first thing we're going to do? Put the what? Centimeters on top. Put the units in their place, meters on the bottom. Now match numbers with units. How many centimeters in a meter or how many meters in a centimeter? 100 centimeters is 1 meter. You got it. So when you multiply 100 times 20, and they write in scientific notation, that's 2.00 times 10 to the third, because you move that 1 decimal there, this 2 decimal places there, that's 10 to the third centimeters. Now we can use our resistance formula. R is equal to rho, which is 1.72 times 10 to the minus 6 ohm centimeter times length, and that we just found out is 2.00 times 10 to the third centimeters. We just converted that, okay? Divide that by the cross-sectional area, which was 6.56 times 10 to the minus 3 centimeter squared. And by the way, that's really small, okay? Very small cross-sectional area. Okay. Now, I'm going to do a few things with exponents. I hope you won't get too confused by this. When you divide one exponent, one base with an exponent by another same base, different exponent, you subtract the exponents. Keep the base, subtract the exponents. Okay? So that's going to give us 1.72 times 10 to the minus 6 ohm centimeter. And I'm going to just do the exponents here. 3 minus a minus 3 is 6. 3 plus, minus a minus is plus. So that would be this 2.00 times 10 to the 6 centimeter. Okay? I'll just move the exponents up there. 6.56. And we don't have these here because I already took care of that. That's centimeter squared. The units don't really matter that much. I just took care of the exponents. Now, when you're multiplying same base, different exponents, you add the exponents. When you divide, you subtract the exponents. When you multiply, you add the exponents. And when you add a minus 6 to a plus 6, you get 0. So you lose your exponents altogether. And that winds you up with just the numbers. 1.72 times 2 divided by 6.56. So if you just punch the numbers in. Now you can do scientific notation and do all that, but I was just saving you a bunch of button pushing by showing it's just the numbers. But you can do the scientific notation, do these just as you read them, and it works just the same. So what do you get? 1.72 times 2, that's 3.44 divided by 6.56. What does that give you? 3.4. Say again? 524. What unit you reckon? Here, the centimeter and centimeter, those goes you centimeter squared divided by centimeter squared. They disappear. And that just gives you ohms. 0.5 ohms. Okay? And that would be the 0.524 ohms. That's the resistance in that copper wire. Now, that's half an ohm. Doesn't seem like a lot, especially if you consider this is a piece of copper wire 20 meters long. Okay, 20 meters? That would be, think of it this way, I'm about 2 meters tall. The ceiling's about 3 meters tall. A 3-story building would be about 9 meters tall. Let's call it 10. So a 6-story building, that's the length of the copper wire, and it only has just over half of ohm resistance. That's a pretty good conductor. Okay, and it's a very tiny cross-sectional area. Okay. Now, there was nothing in our course description that said we needed to do Ohm's law, but basically we've talked all around it. Oh, and by the way, that finished section 17.5. You could do any of the odd number exercises 1 through 9. Those are those answers are in the back of the book. Okay. Now let's go to 17.6, Ohm's law. Not going to spend a lot of time on it, but we've already done it basically, so I don't think it hurts to go back and re-emphasize it. Okay, again, Ohm's law, developed by Georg Simon Ohm, a German physicist. Okay, I have a little blurb about him here. Actually born in Bavaria, which is near Munich. Okay, so that's southern Germany. And they named the resistance ohm after him, as we've already said. And he found that for many materials, the current voltage relationship is basically linear, a direct proportion. Some nonlinear materials, like semiconductor diodes, they go a curve type thing. So at certain voltages, they go up very fast. The current would. At other voltages, they'd be very, very slow. Okay? So here is Ohm's law. We actually have already done it before. Sorry. I gave it to you before. V is equal to IR. That's one form of Ohm's law. But using your little circles or triangles, can you give me two others? R is equal to V over I, you got it, or I is equal to V over R, you got it. Those little circles or triangles will give that to you every time, okay? All three of those are forms of Ohm's law, okay? Now remember, occasionally they'll use, instead of V, they'll use E for electromotive force. Most of the time, we'll use V, voltage drop, okay? Now, in terms of units, current is measured in amperes, voltage is measured in volts, that's the one that uses the same symbol, and resistance is measured in ohms. So an amp is equal to a volt over ohm, a ohm is equal to a volt over an amp, or a volt is equal to an amp times an ohm. Okay, any way you want to do the units as well. All right. Now, the question is do we have time for one example? Probably not. Let's try to get one in. A heating element on electric range operates at 240 volts. What's that a measure of? Easy answer. Your volts, exactly, okay? Remember that unit and that parameter are the same. Has a resistance. What is the symbol for resistance? R is equal to 30.0 ohms, okay? What current does it draw? So we're looking for I. That's the unknown. How do we get that? A V over R. And V is 240 volts, and R is 30.0 ohms, and that's going to give us, now I'll show you an easy way to do this without the calculator, but if you want to use a calculator, you can. Move this decimal, both of them one place to the left. 24 divided by 3 is 8. And what do you measure a current in? Second, amperes. Okay, but we got 3 significant digits, so put the 0.00 by it. 8.00 amps. Okay? No, they only did 8.0 amps. Ah, here's why. They didn't tell you that that digit was significant, and since they didn't tell you that, you have to assume it's only 2 significant digits, so this would only be 2 significant digits. They're really picky about their significant digits. As you'll notice, I'm not that picky about it. Okay. So 8.0 amps. That do it, or do we have time for one more? Okay. All right. I figured you were going to say that. We'll pick up next time with example 2, and that basically we're almost through with Ohm's law. I told you it was really short. You can start working some of the problems 1 through 15. You don't have to do them all. We'll finish example 2 next time, and we'll get started on series circuits. And that's one that the course description did say you needed to do. All right, any questions?